The following program is part of Cable in the Classroom, a free service of the cable telecommunications industry and your local cable company.
Grab some extra batteries because Assignment Discovery is about to plug into the world of energy in understanding electricity.
First, you'll learn how electromagnetic waves can turn a blank screen into a window to the world as we tune in to TV.
Then explore the many ways people harness the power of the electron, from lightning rods to Las Vegas, in electricity's power.
And finally, discover how engineers are tapping the globe's natural heat to create cleaner power for our modern world in Energy from the Earth.
Sparks are gonna fly. Coming up next.
As you watch the first half of this program, keep these questions in mind.
How does a television signal travel?
What is the difference between a conductor and an insulator?
TV images make quite a journey to get from cameras in the field to the screens in our homes. As electronic signals, they can travel thousands of kilometers in an instant and paint a picture in the blink of an eye.
What do you like or dislike about television?
I like that for TV you get plenty of entertainment.
Well, there are certainly some shows on TV that can provide you with information to know more about what's going on around you.
I like to watch TV to relax.
I like the realism of TV.
I definitely like reality TV. I'm a big fan of that.
What I don't like is that it can have a negative influence on its audience.
Commercials all the time.
Well, I dislike that there are a lot of the same things on.
You start kind of becoming addicted to it.
When, like, you look up at the clock after a while and you see that it's been like 2 hours and you could have been doing other things that are probably better for you.
Television sure has changed since the first black and white images were transmitted in 1939. Today, you can ride with the driver inside race cars. Then the next minute, stand on the track as they hurtle toward you. And without batting an eye, you can float across the track, free as a bird. It seems so easy, we forget we are looking at a triumph of technology.
Nice shot. Beautiful. Wait. Stay on this. Ready, set.
The triumph in this particular case looks like a large metal mosquito. The object can swoop across the field because somebody came up with the idea to install a camera in the nose of a remote control helicopter. And then somebody else figured out how to transmit the camera signals from the helicopter to the control booth. The cars at Daytona whip around the oval at an average speed of more than 300 kilometers per hour. But that's a mere crawl compared to the video signals that bring you pictures of the race, which travel at almost 300,000 kilometers per second. Let's follow the video's electronic race from the track to your television screen. First, light images entering the aerial camera are converted into flowing electrons, the first of many changes for the signal before you finally view it. Next, the electrical signal is transformed into microwave radiation and is beamed from the tiny helicopter to a technician holding an antenna on a pole. Here, the microwave signal is changed back to a flow of electrons that moves through a wire to TV monitors in the director's booth.
Flying cam. Ready, 25.
The signal is then beamed as an electromagnetic wave up to a relay satellite, and then relayed in the same form down to the network control room in New York City. Then the signal goes back up into space through another satellite link and is received by local television stations. At the local station, the signal is transformed once again into an electron stream sent on a short trip through wires to the top of a nearby transmission tower, where it is converted into a television broadcast signal. That signal, in the form of an electromagnetic wave, is received by antennas at millions of households. For viewers hooked up to a cable television service, the signal will also be captured by the cable company's satellite dishes and can be converted into laser light that travels down long strands of glass, called fiber optic lines, to your home. All TV signals, no matter where they come from, enter your TV set as a flow of electrons, electricity. Specialized electronics inside the television set use that electrical signal to paint the viewing screen with a beam of electrons, line by line or dot by dot, so quickly that your eyes don't notice it. All the excitement, drama, the death-defying thrills on television come down to electrons generating an image we can see. The first experimental television sets used a beam of electrons about this large, which resulted in a very crude picture. Later television sets used a smaller beam that could paint more lines and show more detail. Until recently, ours has been an analog world. Analog signals can vary in strength, so analog transmissions can be distorted easily. Digital technology eliminates many of the problems associated with analog signals. Digital pictures and sounds are clearer. Digital technology not only improves the quality of pictures and sound, but it also takes up less room within the cables that carry the signals to your home. This creates space in the cable for hundreds of new channels. Today, advancements in the field of electronics mean that we constantly have new and better ways to watch television. High-definition television, or HDTV, is the latest format for broadcasting programs. The pictures are noticeably superior to the audio and video seen on analog sets. We can watch HDTV on the new generation of sleek, stylish plasma television sets. Like the widescreen movie formats, the size of an HDTV picture is much closer to the way we see. Our field of vision is more rectangular than square, so when we watch television in widescreen format, it has a stronger visual impact. Besides a wider screen, the picture on HDTV has more detail and crisper images. And surround sound makes you feel like the sounds coming from your TV are all around you. Advancements in the field of electronics are happening all the time, but it is expected that within the next few years, almost every household in the United States will be watching high-definition television. Did you know Philo T. Farnsworth, the inventor of electronic television, was the son of an Idaho potato farmer? The neatly plowed rows in the fields gave Farnsworth the idea to create pictures using a series of thin parallel lines.
From lightning bolts to power lines, electrons are moving all around us. By studying electricity, we have learned how to use its energy and how to avoid its dangers.
What modern inventions use electricity or electronics?
Things that use electronics is like a calculator, my cell phone, when I go on the internet.
Kitchen appliance and a CD player.
And the computers and TVs, you can find them even on farms now, using to grow things.
With a pacemaker, it's great for in case people have heart attacks.
And Walkman, Discman, MP3 player.
All products today is kind of like an organizer. When you make a phone call now, like it's all electric, and like before you had to like dial and like an operator.
Well, now they have electronic dogs and cats.
It's just basically like how we get by, so it's in everything.
Long before we knew what it was, long before we harnessed it, electricity rose from the ground and fell from the heavens. Even our bodies have their own electric system.
So there's constantly current flowing into the earth from thunderstorms and flowing out where there's not thunderstorms. And in that process, an electric field is generated in the atmosphere. We walk around, the voltage between your head and your toes when you walk around is 200 or 300 volts, and nobody notices that because you grew up in it.
But when there is enough electric energy built up between the clouds and the Earth, it's hard not to notice. One of those who was fascinated by the phenomenon was Benjamin Franklin. During a storm in 1752, Franklin used a kite and a key to prove lightning is a form of electricity.
Ben Franklin was a really smart guy. He was one of the original experimenters with electricity, period. He, in fact, invented the designation of positive and negative charge.
Today, high technology has replaced the kite. In north-central Florida, scientists summon lightning and bring it to the Earth with a rocket and a wire.
We can make the cloud produce lightning and direct it where we want to direct it to do tests, and that really hasn't been possible before.
They direct the lightning to strike simulated houses and power lines to understand what happens when it hits. The rocket launch provides a more controlled experiment than anything Ben Franklin could have imagined.
Well, we do similar things. He didn't think his kite was going to get struck, and he thought that if it was going to get struck, that he wouldn't get hurt. So he was wrong there. If the kite had been struck, he probably would have been killed, as have many people flying kites.
The scientists load a rocket and launch it into the belly of a thundercloud. From the rocket's tail, a spool of copper wire unwinds, creating a path for the lightning to follow.
There's a level of excitement and tension before you push the button, and then there's a level of holding your breath for 2 seconds when the rocket goes up that's unlike anything else. And success feels real good because we only make it happen 20, 25 times a summer, so every one is a big deal.
It's like a rocket-powered lightning rod. Once the wire is shot up into the air, the lightning hits it. In an instant, the electric current of the bolt moves down the wire, disintegrating it into a green vapor.
What flows down the lightning at 50,000 amps is the same thing that flows in your wall at 10 amps.
The temperature of a lightning bolt is more than 27,000 degrees Celsius, 6 times hotter than the surface of the sun. All that heat and light is generated by uncounted numbers of electrons being forced to move. An atom's nucleus has a positive charge. Electrons orbiting the nucleus have a negative charge. When electric current flows, electrons are torn from atoms and move freely.
Electricity is the flow of electrical charge, and most of the charge flows as electrons moving.
Whenever there's an oversupply of electrons, an object develops an overall negative charge. Nature balances things out with equal positive charges somewhere else. The potential difference between the charges is measured in volts. Electric current, anything from static electricity to lightning bolts, is electrons moving from negative to positive.
It seems like it's easier to make sparks and lightning than not to make them. Anytime you have two dissimilar materials rubbing together, you get sparks.
The path that leaping electrons follows depends on the material they flow through.
The human body certainly will conduct current, but not a lot. Not like a piece of copper.
Copper electrons face little resistance jumping from one atom to another. Copper is a good conductor. Clay and rubber resist attempts to pull away their electrons. Materials like this are called insulators. How electrons begin to move in the first place is a result of a force of nature called electromagnetism. Our whole technological civilization exists because electricity can make magnetism. And magnetism can make electricity.
It goes back to the fact that we have two kinds of forces that are present that we call electricity or electromagnetism. And those two forces are the electric force and the magnetic force. The fundamental charges are a positive charge and a negative charge.
To see these forces at work, head north and look up into the night sky. Basically, the northern lights are the result of electrically charged particles from the sun colliding with the molecules in the Earth's magnetic field. There's electricity out there.
5, 4, 3, 2, 1. And we have liftoff of the Space Shuttle Columbia, continuing space research through tether satellite technology.
One of the space shuttle's missions during the 1990s was a bold attempt to harness the power in the atmosphere. They generated electricity with a satellite and a wire.
Good work. Let's make sure we stay that way. Understand.
The mission was part of a new experiment of tethering satellites in space.
Verification. 3-14. Go ahead.
The experiment was based on the simple principle that when you move a conductor through a magnetic field, electrons start to flow. This generates an electrical current that can flow through a circuit. The satellite was thrust into space using small gas jets and a 21-kilometer-long cable.
If you put a wire inside of that tether, you now have a moving wire that moves across a magnetic field. That magnetic field in this case is the Earth's magnetic field, and the motion is the motion of the space shuttle moving at very fast, high velocities, orbital speeds.
Things look fine down here, Jeff.
The moving wire in the Earth's magnetic field generated 3,500 volts, enough energy to power a space station.
Okay, we see the tension go way down, but the tether's still going out fine. Very slight lateral oscillation.
The satellite was clearly visible from the ground. With its tether deployed, it became the largest man-made structure ever flown in space. For 5 hours, the tether swept through our planet's magnetic field, generating more and more electricity.
At the boom. The tether has broken. It is going away from us. Get it on the TV, Claude. Please get it on the TV. The tether has broken.
Copy.
Trying to photograph it floating away from us.
Looking back, we quickly saw that, in fact, the tether had broken. This was it's a big shock. It's kind of an empty feeling in the pit of your stomach when you look and you realize that there is the tether moving away from us at about 80 feet per second, and you just wanted to reach out and grab it.
The wire was generating so much electricity that a spark jumped from the wire to the satellite deployment system and burned through the tether. The $440 million experimental satellite just drifted away.
Yes, sir. Well, those are some tether dynamics we did not want to see.
Well, we have demonstrated that you can generate a lot of electricity with tether, and unfortunately we've also demonstrated that you can use tethers to launch a satellite into a much higher orbit.
Perhaps we notice electricity most when we don't have any. New York City has experienced 4 major blackouts in the past 40 years. For 25 hours beginning July 13, 1977, New Yorkers were without lights or elevators or alarms. Lightning had knocked out power lines north of the city, and the utility company's backup equipment malfunctioned. In the United States, 98% of homes and businesses receive power from a grid, a vast electrical system that is woven together with a web of power lines. These power lines are live wires carrying 500,000 volts. It's up to the line workers to inspect and repair every part of the grid, usually without shutting down the power.
It's pretty dangerous, I feel, because you're mixing aviation with electricity. One, you're depending on the helicopter, everything mechanical to go right. If it goes wrong, you're going to drop out of the sky like a rock. If the lineman makes a mistake, you're going to vaporize.
These line workers and pilots work for Agroders Incorporated. It is one of the few companies that attempt these high-wire acts. It's dangerous work that only a handful of people in the world are qualified to do. One of them is Spider Lockhart.
It goes over top of that because I'm going to put the hood over top of my helmet.
The dress required for the job is a lightweight suit of armor made of stainless steel thread.
It's tied in with it. We have a strap on the inside that ties to the pants, making an electrical connection between the pants and the jacket.
Electricity follows the path of least resistance. In this case, the metal threads of the suit rather than the body of the worker.
We're dressed in a stainless steel suit, fully conductive, fireproof, Nomex. Everything we have is fully conductive.
Have you ever walked through a hotel room with a certain pair of sneakers in the wintertime where you walk up to your hotel room door, reach over and grab the door, and you get a little zap on you? That's called static electricity. Basically, that's what I'm trying to eliminate from what I'm doing.
The dangerous marriage between helicopters and power lines is made to save money and time. Repairs that take a conventional ground crew days, Agroders completes in hours.
Bill, we're just looking for the right structure number, and then we're going to have to probably turn back a span or two once we orient ourselves.
The lineman's life depends on a constant communication between him and the pilot.
This is the span that we want. I'm going to go ahead and come down in between the two 500 kV lines, and we're going to find the damage location, and we'll get ready to start work.
We could actually get too close to a power line and a tree, and the electricity would arc amongst all of us, and we could actually short out the power line and destroy ourselves.
Both men know if the communication stops, something is wrong. It's a crucial fact that Spider Lockhart learned from experience.
As soon as I felt the voltage going through me from the mechanical ground that I had, I knew that I'd made a mistake. Sometimes it's a little bit late to figure out your mistakes, but I knew that as soon as I felt that. I had enough to know that it was killing me, and to me, I was screaming to the pilot to get me away from the wire, and he never heard a thing because I couldn't open my mouth.
The electricity stopped Spider's heart, but a coworker revived him. When Spider is suspended in air and therefore not grounded to anything, the electricity treats him as part of the wire and safely passes over his body, not through it.
If you were able to take a voltmeter, which measures voltage, and measure the voltage on that helicopter, it would be energized at 500,000 volts, and anything on that helicopter.
The metal wand gives the electricity a controlled pathway from the wire to the helicopter. Once the pathway is established, the lineman replaces the electrical connection held by the wand with metal clamps. The clamps allow the lineman to free his hands so that he can work. The amount of voltage may be the first fact recited when explaining the dangers of electricity, but the high voltage isn't what kills a person. It's the amps. The electricity in the lines can flow at 500,000 volts, but isn't necessarily deadly if the amps are low, real low. It only takes 1 amp to stop the heart. Think of the electricity flowing through wires as being like water. In a squirt gun, water is under pressure and moves fast, but you probably wouldn't want to use it to put out a fire. It's not the pressure that's the problem. It's the amount of water. You need a fire hose that can move a whole lot of water. The water pressure is equivalent to voltage in electricity. The amount of water is like electrical current and is measured in amps. Multiply volts times amps and you get watts. It takes 100 watts to light a bulb. 1,000 watts equals 1 kilowatt. Hoover Dam produces 4 billion kilowatts a year, electricity that's sent to California, Nevada, and Arizona.
This is the Arizona wing of the power plant. This room is longer than 2 city blocks. We have 9 of our commercial generators in this wing, each producing 16,500 volts of alternating current. Each generator can supply enough electricity for a city of 100,000.
The power of falling water spins the blades of a turbine. The shaft from a turbine spins a magnet inside a tightly wound coil of wire. This motion generates electricity. The spinning magnet causes electrons to move in the wires and produce an electrical current. In this case, it's alternating current.
A direct current flows directly without any pulsations. It's just a direct current. It's exactly what it is. It's like if you open a pipeline and let the water flow in one direction. That's direct current. And the word direct means just that, and that's exactly what it is. Alternating current means that the electricity flows to the load and back to the generator, to the load and back to the generator, and the frequency that this happens is called cycles.
The generators produce 16,500 volts of electricity. Before it leaves the power plant, the electricity's voltage is increased or boosted to 230,000 volts for long-distance travel. At the other end of a line, the process is reversed, and the high voltage is stepped down to 110 volts and delivered into millions of homes.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How does a television signal travel?
What is the difference between a conductor and an insulator?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
As you watch the second half of this program, keep these questions in mind.
How do doctors use electrical signals to treat heart patients?
How is mechanical energy converted into electrical energy?
The light bulb was invented more than 100 years ago, and it's hard to imagine modern life without it. But people are still finding new places to use electrical power, like in remote jungle villages, or even inside the human body.
What would you do without electricity?
Without electricity, the days would be shorter.
I'd have to go to bed at 7 o'clock, couldn't listen to the Walkman or the radio.
Yeah, I wouldn't be able to go online, watch TV, talk on the phone.
Open the refrigerator, use the microwave.
Heating, air conditioning.
I'm not sure exactly what I'd do for entertainment. I'd probably spend a lot more time outside.
I'd probably spend my time inside reading a book, drawing, arts and crafts, things like that.
I would tone things down and try to live a more simple life and really try to become more familiar with natural things like nature.
Las Vegas.
Well, people are like insects. They just love light, and they're drawn to it, and they want to see what it's all about. And so the casino operators and everybody here put a lot of light out, and it just draws people in. It just says, we're having a party here. Come on in. Come on in.
In Vegas, the theory is, if you build it, they will come. And if you build it and cover it with lights, they will come and spend money.
Without electricity, this town would just be another sleepy place in the desert.
From space, it's the brightest man-made spot on the planet. Millions of bulbs that all, at one time or another, burn out and need to be changed. Every night, crews from the Young Electric Sign Company go to work repairing and replacing bulbs. One of their biggest jobs is on the Fremont Street Experience. On a grid above pedestrians shine 2 million bulbs and a $70 million light show. The town never shuts down, but things are a little slower after midnight. That's when the crews test the system and make repairs. It's Homer King's job to change the bulbs.
It should be dim now like the rest of these. That way the computer will tell it how bright to go. These bulbs have a life expectancy of 25,000 hours. I'm on a roll tonight here. Let's try that again.
A light bulb lights because its filament offers some resistance to the flow of electrons. As the electrons try to crowd through a hair-thin tungsten wire, the energy spent overcoming resistance turns into heat.
A material that's resistive is one that requires some kind of work to push the charge across. That means you're giving up energy that turns into heat and will heat that element up.
And here, heat means light. The filament reaches a temperature of about 2,500 degrees Celsius. On Fremont Street, the bulbs burn bright.
Okay, hey, Art, will you go ahead and change color?
7 shows a day, 7 days a week, and nothing stops the display except for thunderstorms.
People ask us all the time, does this keep rain out? Well, no, it doesn't keep rain out. Water doesn't really hurt it. What hurts is this lightning. We got 30 computers on the other side of this frame. So when the lightning's there, we shut it down.
The Fremont Street lights are controlled by 121 computers. It's the largest outdoor sign in the world, towering 27 meters high and running the length of nearly 5 football fields.
Hard Rock, this is one of my favorite properties here.
Not all the lights in Las Vegas rely on incandescent bulbs. Neon and fluorescent lights use electricity to excite atoms that glow instead of heating up a thin wire. The signs may change, but using light to attract crowds has been around since electricity was harnessed. As soon as scientists were able to capture electrical energy, they began to experiment with it. In 1780, an Italian anatomist, Luigi Galvani, made groundbreaking discoveries.
Galvani made lightning measurements. Galvani took frogs' legs and showed that when it lightened, they twitched. So he showed that the lightning radiates an electric field which produces a voltage on the frog legs.
Throw the switch. Wait, I thought I saw a pulsation of a part. Dr. Bradshaw is beginning to breathe. You brought this man back to life. No. The heart muscle simply responded to a terrific electrical shock, that's all.
What was once thought to be science fiction turned out to be fact. A heart beats because every second electrical impulses spread through the heart muscle, triggering and coordinating a movement. These signals send echoes through the body tissue to the skin, where they can be detected by metal sensors and displayed as an electrocardiogram, an electrical readout that allows doctors to constantly monitor the heartbeat.
Electricity and electrical impulses are all over the body.
The electricity in our bodies is created by chemical reactions between cells.
What triggers the heart to squeeze are these signals, these small electrical currents, which travel from the outside to the inside of the cell every time your heart beats.
Dr. Hugh Calkins is an electrophysiologist at Johns Hopkins University. He uses electricity to treat and cure electrical malfunctions of the heart. Today, he is implanting a device in a patient who suffers from a condition that causes the heart to beat too fast.
It takes a certain amount of time for the heart to squeeze blood out of the heart, and also for blood to get back into the heart. So if you go very, very fast, instead of squeezing in a rhythmic fashion, it will literally be quivering, and no blood will flow in the body. And within seconds, you'll pass out, and minutes after that, you'll be dead.
In order to restore the heartbeat, the victim needs an electrical shock.
When you just put these on the body, you get what's called a quick look, that this acts as an antenna. You can see what the heart rhythm is, and if it's not what you want it to be, if it's ventricular fibrillation, then you can go ahead and discharge it. The way that's done is by pushing both of these buttons simultaneously will cause these to fire, and that will give a 360 joule shock across the body. And to the degree that the heart's in between, the heart will be depolarized and normal rhythm will be restored.
In the electrophysiology lab, the technology of portable defibrillators is now being implanted in the body. Calkins threads a small wire lead down into the heart.
And that's up in the pulmonary artery.
The wire lead acts like permanent paddles on a heart. If the implantable defibrillator detects a problem, it will automatically give an electrical shock to the heart within 10 or 15 seconds.
When I put one of these in, you really have this comforting sensation that this patient, it's like as if they're in the intensive care unit forever, that if ever they develop a rhythm abnormality, too slow or too fast, it will take care of it. And it's really this tremendous insurance policy.
The most critical part of the procedure is the testing of the device.
Here we go.
The patient is given a shock that puts his heart into overdrive. The heart starts fluttering rather than beating steadily. Ventricular fibrillation, they call it. Unless corrected quickly, it can lead to death. It's the only way to test the device.
When we were putting in the defibrillator is when we induced this ventricular fibrillation, this very fast heart rhythm. You saw a lot of very rapid squiggles on the screen, and that was the heart beating very, very chaotically with multiple short circuits swirling around the heart, resulting in the heart beating 400 or 500 beats a minute.
The trick is to customize the implantable defibrillator so it delivers the lowest level of energy that can still get the heart beating back to its normal rhythm.
Okay, so that's it. There's more and more enthusiasm about the benefits of electricity. I know for many, many years there was a lot of debate over, was it better to treat patients with sudden cardiac death with medications or with defibrillators? And now the studies are available showing that defibrillators are better than medications, at least the medications we have now. So there's a case where electricity won, where electricity was better.
This is a Utah arm, one of the newest links between human and machine. The device uses the body's own electrical impulses to operate and control an electrical arm. John Migueles works with amputees, teaching them how to use and operate the arm.
Right now, there's a race between limb transplant and electronics. We start off with a silicone skin, and inside it there are electrical motors that control the opening and closing of the fingers. Next, very often we have a electrical motor here that operates wrist rotation, supination or pronation. Then we also have an electrical motor over here that controls this transmission that you can see that controls flexion and extension of the elbow. The microcomputer is mounted right here, and that processes all that information.
Bob Goodman controls his bionic arm by contracting his biceps and triceps muscles.
I like to grab my brother's hand and squeeze and kind of watch his eyes a little bit. Maybe that's a little bit of bionic feeling.
Ironically, it was electricity that destroyed Bob Goodman's arm in the first place. He was on a roof removing a television antenna when something went wrong.
This antenna became top-heavy and came in contact with high voltage lines in back of us, some 12,500 volts. It was an aluminum ladder that I was on, and so it became very hot and burnt my leg. Luckily, I was knocked loose of the ladder and hit the ground, because some of the doctors think, well, with that amount of volts, your heart probably did stop. When I hit the ground, it kind of jump-started my heart again.
When the brain sends an electrical signal to flex the arm muscles, the signal or impulse is intercepted at the muscle site by electrodes or skin sensors. This electric impulse is then amplified and used by a microcomputer to control the electrical motors in the arm.
The patient has to be able to produce two independent signals or muscle contractions. Typically with Bob in this situation, we're using biceps and tricep muscles, but he has to be able to fire those independently. If he were to fire them together, it would tell the hand to open and close at the same time, which would just create a little jitter in the hand.
In a myoelectric arm, when you lock the elbow here to make the hand work, to unlock this elbow, it takes the flex of both muscle sites at the same time and then an instant relaxation. So for me to get that elbow to unlock, it took quite a few months, actually. I would always flex one site before the other. So it was releasing the elbow is what took me the most time to get down.
So how are things going? You having any particular problems?
Not really. I've put a new harness on and snugged up the fit in my socket, so it seems to be responding really well.
Great. How's that battery doing?
Well, I'll turn this arm off here, and the batteries are holding up real well. This new battery pack is lasting 4 to 5 days for me. A lot.
Okay.
It's opening and closing the same amount of effort for both. Just open this and clean this. I've chosen to wear this arm every day, so maybe I didn't learn quite enough lesson from an electrical shock, because I still wear an electrical arm.
Okay. Good for another 10,000 miles.
Yeah.
The modern world would be inconceivable without electricity. In 8 hours, a man used to hard work can continuously exert 1/10 of a horsepower, but the same amount of work can be done by an electrical motor in a fraction of the time. Electricity as a harnessed power has no rival. It is clean, silent, and can be turned on and off instantly. Worldwide, there are still 2 billion people who exist without electrical power. Most are located in remote places like the Brazilian village of Boa Sorte. Too isolated to receive power from the country's grid, the residents are without the electrical inventions of the 20th century and without conveniences like medical vaccines that need refrigeration, electrical motors, or clean running water. The villagers used contaminated surface water, which was funneled from the springs to the local watering hole. The only clean water was buried deep beneath the earth. An electrical pump was needed to get the water to the surface. To solve this problem, the governments of Brazil and the US joined forces to provide electricity by harnessing the sun's energy.
Putting up power poles and lines is so expensive that actually photovoltaic energy is much cheaper here than using traditional forms of fuel.
Photovoltaic cells, or solar panels, convert energy radiated by the sun into electricity. It is clean, renewable power that villages like this can afford. Engineer Roger Taylor is part of the electrification initiative in Brazil.
In this particular village, they're going to change by having the school accessible at night. The health clinic will certainly be able to store vaccines and provide more immediate health services. And the water pumping system here, particularly since it's so deep, will provide very pure, very clean, filtered water.
The joint effort will set up 4 different systems here. The largest will power an electric water pump for the well.
Water pumping takes a fair amount of energy in this case because the well is fairly deep. The well here, we will put the pump at about 100 meters down in the ground, so it takes a lot of energy to pump that water up to the top.
When a solar panel is put out into the sun, the materials within it release electrons and produce electricity. In Boa Sorte, the panels are being connected to a pump. When the system is up and running, the electric current and water will flow. And the village will celebrate the day the power was turned on. Technological advancements that took 100 years to develop arrived here with the flick of a switch.
And so then it'll be very interesting to see, once they have the basic standard of living that many people of the rest of the world enjoy, how their lives and their culture will evolve from that.
More and more aspects of our world depend on electrons in motion. They flow through countless switches and machines. They flow through our bodies and brains. When Ben Franklin stepped out into a storm with a key and a kite in 1752, he could never have imagined the way electricity would revolutionize the world. Did you know? The brightest man-made spot on Earth seen from space is Las Vegas, Nevada. But long before Vegas got its sparkle, Coney Island in New York was called an electric Eden. In the early 1900s, more than 1 million incandescent light bulbs illuminated the island's amusement parks.
The electricity we depend on comes from many sources. Some are harmful to the environment, while others use the natural energy within the Earth itself to power our world.
What kinds of electricity are there, and where do they come from?
There's windmills that, use the power of the wind and harvest it into electricity.
Lightning creates like static electricity.
Science centers, there's sometimes big balls that you can put your hands on and they make your hair stick up, and that's cool.
You can use water to create electricity.
We can generate electricity from like solar panels on the roof.
Fossil fuels, I think, and water and air, and who knows where else.
Energy doesn't come from any particular place. It's just the movement of particles in the universe.
Ever since reliable ways of generating it were discovered, electricity has been a part of people's lives. The key to producing electrical power lies in understanding the connection between electricity and magnetism. This connection may have been first observed aboard ships at sea. When ships were hit by lightning, a form of electricity, their magnetic compasses swung wildly. In 1820, a Dane named Hans Christian Ørsted conducted an experiment showing the relationship between electricity and magnetism. He placed a compass next to a wire that was attached to a battery. As an electrical current flowed in a complete circuit through the wire, the compass needle moved. Ørsted had shown that an electric current can generate a magnetic field. In 1831, English scientist Michael Faraday showed that a wire with an electric current running through it could make a magnet rotate. This phenomenon is called induction, and its discovery led to the invention of the electric motor.
I got it.
You got it?
Yeah.
We have a motor.
10 years later, Faraday made a second discovery. He found that moving a magnet in and out of a coiled wire created an electric current in the wire. This discovery led to the invention of the electric generator and became the foundation of our electric society. Electric generators produce most of the electricity we use today. Most of these generators depend on spinning turbines to generate electricity. A turbine is a mechanical device that uses a flowing substance, such as air, water, or steam, to push against blades and turn a shaft. As the blades turn, they spin a shaft attached to a magnet. The magnet is encased in a tightly wound coil of wire. As the magnet spins, its magnetic field causes electrons to move in the wires, inducing an electrical current. The mechanical energy of the moving blade has been converted into electrical energy, which can be sent over electrical transmission lines to locations hundreds of kilometers away. Blowing wind, flowing water, and even ocean tides can be used to turn turbine blades and generate electricity. But the most common way to generate electricity in the United States is to turn turbine blades using steam. Most of these generators create the steam they need by burning fossil fuels like coal, oil, and natural gas, or by heating water using nuclear reactions. But these methods create harmful byproducts. The burning of fossil fuels creates pollution and may contribute to global warming. And nuclear power plants generate long-lasting radioactive waste that is dangerous and difficult to dispose of. But one of the cleanest ways to generate steam is by harnessing the energy of the Earth itself. This type of energy is called geothermal energy. Geothermal energy forms as heat inside the Earth creates vast underground regions of hot rock. When these hot areas of rock come into contact with underground water, they can form geothermal reservoirs that can reach temperatures 3 times the boiling point of water. We can tap into this natural heat and use it to produce electricity by building geothermal power plants nearby. Geothermal energy can be found in 3 different forms, as dry steam, hot water, and warm water. Dry steam reservoirs, which produce steam and only a little water, are the most valuable kind of geothermal energy. Dry steam power plants tap into this naturally occurring steam and pipe it through a turbine, where it spins blades attached to a generator and produces electricity. The steam is then condensed and pumped back into the reservoir, where it starts the process again, without producing harmful emissions. Geothermal reservoirs of hot or warm water are more common and can also be used to generate electricity in a similar way, but they're generally less efficient than dry steam reservoirs. Today, geothermal power plants supply electricity to about 4 million people in the United States. But nearly 90% of America's electricity still comes from plants using fossil fuels or nuclear reactions to create steam. Worldwide, though, geothermal power plants produce about 7,000 megawatts, providing electricity to about 60 million people in 21 countries. The geothermal reservoirs we already know about could produce thousands of megawatts more if they were tapped. And no one knows how many other reservoirs there may be that haven't been found yet. So as people's energy demands grow, alternative sources like geothermal energy are likely to play an increasingly important role in the world's energy production.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How do doctors use electrical signals to treat heart patients?
How is mechanical energy converted into electrical energy?
We hope you've enjoyed this assignment discovery, Journey into Electrical Energy. If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
That's a wrap for today, but tune in next time as we dive into the dangers of the deep. We'll break down the fluid forces behind the Titanic disaster. Search through another underwater shipwreck looking for clues about its demise. And learn the devastating effects that water pressure can have on the human body. Join us next time for Underwater Forensics, here on Assignment Discovery.
The preceding program is part of Cable in the Classroom, a free service of the cable telecommunications industry and your local cable company.